Welcome to this explainer, brought to you by Forge College. All right, we are standing on the final assembly line today. Over our past few sessions, especially that deep dive into optimization and error handling, we've been designing, tinkering, and really stress testing individual components. Well, now it's time to build the ultimate Capstone smart contract. We're going to take all your hard work on data types, structs, and mappings and literally forge them into a single, comprehensive, compilation-ready deliverable. If you've ever felt that absolute thrill of clicking scattered puzzle pieces together into one cohesive masterpiece, you are in exactly the right place. I actually like to call this phase the Master Inventor's Blueprint. So hello there, fellow inventors. Think back to our previous work. We spent a ton of time crafting these incredibly precise gears and cogs, right? Compact numeric bounds checks, structured revert patterns, gas-efficient storage models. And hey, on their own, they were brilliant little exercises. But today is where the real magic happens. Today, we assemble those isolated parts into the whole shebang.
Okay, let's dive right into our schematic for today. We'll start with the final blueprint, move into building the skeleton, then wire our mappings, run some quality control, give it an AI polish, and finally, make sure we're ready for the next phase. Section 1. The final blueprint. It's time to gather our artifacts.
Before a master builder lays a single brick, they survey their materials, right? You should have these 4 critical artifacts ready to go on your workbench. First up, your type selection spreadsheet. That's where we balanced gas costs against readability. Second, our nested-struct prototype, which basically maps out how our data will be clustered. Third, our validation test suite, packed with assertions to keep bad data out of our state. And finally, those optimization notes, detailing exactly where we can squeeze out precious gas savings. Look, these aren't just old homework assignments. They are the exact raw materials we are integrating right now. Moving on to Section 2, building the skeleton and inserting our data types. With our materials gathered, we're going to start piecing together the final contract skeleton. Think of this like a master watchmaker, slotting in precisely machined gears. We're carefully inserting our optimized data types so everything fits perfectly in the Ethereum virtual machine storage slots. Now, what's really interesting here is the why behind these choices. Take a look at our ID field using a UN32. For a lot of folks, capping out at 4 billion records sounds like a limitation. But let's be real, storing 4 billion records on the blockchain, that's just a casual Tuesday for a well-placed UN32. It is more than enough for our capstone and saves massive amounts of gas. We've paired that with a UN64 for the amount, safely capturing our expected numerical range without the nightmare of an overflow. And for the note, we kept it as a dynamic string. Yeah, strings are definitely more expensive, but sometimes you just need human readability. And for this operation, it's absolutely worth the trade-off. To keep all this data strictly organized, we're using a nested struct. Instead of leaving our variables scattered around like loose screws on a workbench, we group them logically. We take our metadata struct, which holds a compact created at timestamp and a few bit flags, and we just sit it snugly inside the main record struct. Not only does this make the code incredibly clean to read, but it perfectly preps our data for future storage packing. Which brings us to Section 3. Wiring mappings. This is our connective tissue. It's time to wire up your primary logic and see how the data actually flows. Notice the 2 main circuits we're wiring here. On the left, our primary mapping maps a UINT256 ID directly to our record struct. This is our canonical storage, the absolute undeniable source of truth. But on the right, we have a secondary index mapping, an address to an array of UINT256 IDs. Now, why do that? Well, because out in the real world, front-end applications need to easily look up everything a specific user owns. But remember our golden rule. Every extra index increases gas costs. We only wire this secondary ownership index because our specific application demands it. It's a calculated, totally justified expense. Of course, data flowing through wires is completely useless if it's the wrong data. Look closely at this line. Require owner does not equal address 0, throwing the string invalid owner. This right here is our validation checkpoint, and I'm going to give you a massive pro tip. You must keep your revert strings exactly as you planned them. Do not change invalid owner to owner is invalid or bad owner. If you change a single character, your existing validation test suite is going to fail. Stability in your error strings is literally what keeps your testing infrastructure intact. All right, Section 4, Quality Control. Time to run the test suite. We've built the skeleton, we've wired the mappings, and now it's time to run our beautiful machine through a rigorous stress test. Here is our build, implement, and test loop. First, we scaffold our capstone.solve file and our test files. Then, we insert the contract skeleton we just reviewed. Step 3, we compile via our toolchain, so maybe that's Hardhat or Foundry, and let me just share a collective groan for all the developers out there. There is absolutely nothing quite like the universal pain of a red screen of death during compilation just because your pragma-solidity version declaration is like a tiny decimal off from your toolchain's compiler settings. Ugh. But once you fix that version mismatch, you arrive at step 4, running the existing test suite to ensure our logic actually holds up. But hey, we don't just rely on automated tests. We do manual smoke checks too, just to make sure the deployed machine behaves perfectly. You deploy the contract to your local chain. You manually call the create record function with valid inputs. Then, you verify the observable behavior. Did it return the expected ID? Did the record created event emit properly? Finally, you check that secondary index to ensure the ownership mapping actually updated correctly. If all this checks out, your machine is purring beautifully. Next up is Section 5, AI Polish, a little vibe coding refactor.
You know, a master inventor always knows when to ask for a second set of eyes. So it's time to introduce our robotic assistant to give our masterpiece its final polish. This is the exact AI prompt recommended in our source material. Listen to how specific this is. Refactor this Solidity contract for clarity and storage packing. Keep behavior identical. Highlight places to safely change, wait, let me read that exactly right. Highlight places to safely change UN64 to UN32 and explain trade-offs. Notice what we're doing here. We aren't asking the AI to write our code from scratch. Nope. We are using it as an advanced linter. We're asking it to look at how variables are packed into 32-byte storage slots, to squeeze out those last few drops of gas savings, and to clarify our syntax, all without altering the core behavior.
But remember, the AI is your assistant, not the boss. If the AI suggests a cleaner rewrite but accidentally changes a revert string, you will end up with a failing test on the left. That is an immediate red flag context, a broken validation rule. But when you carefully review its suggestions, apply only the safe layout changes, and preserve your logic, you get the glorious euphoric feeling of a perfectly passing test suite on the right. Finally, Section 6, ready for next phase, a review-ready contract. Let's step back for a second. Look at what you've built. We've gone from theoretical concepts to a single, compilation-ready, fully polished smart contract. My fellow inventors, you have successfully assembled your Capstone deliverable. So, the crucial point to take away boils down to these 3 practical principles of smart contract assembly. First, always align your type choices with your documented assumptions. If you assume fewer than 4 billion records, use UN32 and document it. Second, keep your validation strings perfectly stable, because your test suite is literally the only thing standing between you and a deployed bug. And third, treat storage like it's the most expensive real estate on Earth. Only use secondary ownership indexes when your application absolutely requires them. Take a look at your journey across this curriculum. You started in the past with the absolute basics of Solidity from zero. Recently, you mastered data types, structs, and mappings. Today, right now, you successfully conquered the Capstone assembly. You proved your blueprint is complete, your storage layout is rock solid, and your public interfaces are stable, which means next up, you get to tackle function visibility fundamentals. And to get your brain geared up for that next challenge, I want to leave you with this provocative thought. How will changing a single function keyword from public to external fundamentally alter the gas blueprint of your entire invention? Definitely something to think about. Thank you so much for joining me on the assembly line today. Make sure to visit Forge Tech College to continue your Web3 education, explore more deep dives, and keep sharpening those inventor skills. Until next time, keep building and keep learning.